Impact of microphone position measurement error on multi-channel distant speech recognition for intelligibility. Paper number 24, long form, authored by Karan and Sunil Kumar Kopparapu. Quickly, what is multi-channel distant speech processing? You have N speakers and M microphones. Think of it as a meeting, and all the speakers are speaking in some random fashion, and these M microphones are able to record each speaker as a convolution. So essentially, the M microphones that are there are able to get all the people speaking speech into them. And there are two things that you need to do if you wanted to do a multi-channel distant speech recognition. You need to take it through what is called the process of beamforming, where you can get a single channel output script O, which when passed through a general purpose ASR would give you the transcript. So there are two steps. One is the beamforming step, which takes multiple channel input from various microphones and gives you a single channel. And since generally ASRs are working on a single channel, you would require you could use any of the ASR to get your transcript. Now, the problems that usually people look at is two things. One is the process of beamforming, so that you get a single channel output OT, and just one talks about the intelligibility, how good it is, etc., etc. The second important aspect is what is the performance of a speech recognition engine on this single channel speech. So essentially, the whole idea of the microphone position comes into effect. For example, in this slide, you see that for a single microphone and a single speaker, the output of a microphone is convolution of a room impulse response with the utterance, UT, and of course, there is noise effect. So the microphone position or the location of the microphone plays an important role because the room impulse response H is a function of the microphone. The room impulse response is dependent on few constants, LC, etc., which are the room volume, speed of sound, which are more or less constant in a given scenario. And what could probably change is the microphone position. And we'll be talking about what happens to the speech recognition and speech intelligibility when the microphone position is erroneous. So just to take you into the depth, XM, YM, ZM are the microphone locations. And if the epsilon subscript epsilon is the error associated with the microphone, then immediately you see that the room impulse response H calculation is erroneous because of the erroneous measurement of the microphone positions. This leads to the erroneous output of the microphone speech that is given by O epsilon t. So because of this, both the intelligibility and the speech recognition of the output of the microphone get affected. So what we're trying to do, we are trying to see what would be the performance of a speech recognition and also the speech intelligibility when the location of the microphone is inexact, or you do not know what is the exact location. So specifically in our paper, we have looked at M microphones and N speakers, and the idea is to see how a speech recognition engine, a general purpose speech recognition engine, will work when the location of the microphones are not known precisely. So just to get into the problem, U1 to UN are the utterances or the speech of N people, and O1 to OM are the M microphones. Then the output of the microphones is given as a convolution of the room impulse response matrix H and the utterances by the speaker. Or in short form, it is essentially a summation of all the N speakers. For every microphone, health microphone, you would submit over the all the room impulse responses associated with the speaker and that particular microphone. So as we saw earlier, if there is an error in the microphone position, the room impulse response here changes or is erroneous. As a subsequence of that, or a result of that, the output also changes. So here the O1, 1, 2, 3, 4M is the multi-channel speech. So the problem that we are trying to do is when there is we want to look at what is the performance of the speech recognition on this multi-channel. So essentially 2 steps, as we saw earlier: beamforming step, which takes the M microphone outputs and produces one close speech signal. And the other is when the general purpose ASR or the ASR works on the output of the beamformer to get you the transcript. So as you can see in this figure or in this equation, the erroneous input to the beamformer results in an erroneous single channel output, which when transcribed, pass it through the speech recognition engine, results in a transcription which is erroneous. So three things that we'll be looking at. One is the erroneous output from each of the microphones, because as a result of the error in the microphone position, this results in erroneous output, which is the speech intelligibility aspect, and then which is when it is passed through the speech recognition, the transcription. So we analyze two things. One is the speech intelligibility and speech recognition when the microphone positions are inexact. So experimental setup and data for microphone positions as given here in a room dimension of 5 cross 5 cross 5. There are two speakers which are assumed. The lower graph tells you the uh, the instance when one of the speaker is speaking. So when you see a 2 here, only the user 2 is speaking, and when you see a 1 here, user 1 is speaking. So in our case, the first part would be where only the user 1 is speaking, and second part is where the user 2 is speaking, etc., etc. So the data that we construct comes from utterances which are from LibreSpeech clean data set. Then we construct the utterance, which is synthetic, but coming from the real data in the following way, where you take that the U1 is the utterance of the first speaker from 1 to T1 time instance, and U2, etc. Now we know the microphone position as we saw in the last chart. So we can construct H, and as a consequence of H, we can construct the output of the 4 microphones. Now what we do is we say that the microphones are in error. So we introduce a noise in microphone location by introducing what is a Gaussian noise with the zero mean and sigma square variance. This variance sigma is something that we vary to understand what is the influence of this on the ASR. So we construct the erroneous RIR or the room impulse response, and then we construct the output of the microphones. So for speech intelligibility, we compare the output of the beamformer for the clean signal and that with the erroneous signal using two beamformers. One is the delay and sum, another is the minimum variance distortionless response. For the speech intelligibility or speech recognition, we compare the output of the transcripts of general purpose ASR in for both the erroneous and the clean output. So in our case, we use an end-to-end transformer-based speech recognition engine, Alphabet engine. So if you look at the results, as you grow the error, as you increase the error of your microphone, the degree of characters or the alphabets that you get out of the general purpose ASR is going to increase. So here, as you can see in this table, the character error rate increases as the error in the microphone position goes from 0 to 1, 0 indicating that there is no error in your microphone position. So lower the value, the better the idea. So if you look at this, the common observation is the character error rates for both the DSP and the MVDR beamformers. They get higher as there is an increase in the microphone location error. So if you do the computing, you see that for MVDR there is a 3.2% change, while for DSB there is a 10.2% change. This by comparing the character error rate when sigma squared is equal to 1 versus when there was no error. So the observation here is that the MVDR performs poorer because because the way the MVDR is computed depends on the singularity of the inverse matrix which is being used for the weight. So if you look at the errors that are, if you we ran this experiment for about 100 such samples, and then we just plotted this box plot. So what you can see is as sigma squared, that is the error in the microphone position, error increases to 0.5 or more, the variance and the outliers in the CER increases. And especially at sigma squared is equal to 1, that is the last plot here, the variation is sigma is significant. You can see that it is going up and down. Now, what is the impact of noise on speech recognition? This is important because we want to sort of compare that what the microphone location error does. How can you compare it with the environmental noise? For this purpose, what we did was we took the UT as we saw earlier. Then we added some noise, additive white Gaussian noise, and then we computed the transcripts of that using the general purpose ASR with different noise levels. So as one can expect, as the signal to noise ratio or the noise increases, the CER scores will also increase. So this plot shows you what is the impact of the speech record. So the better the signal, that is higher the SNR towards your right, the outliers and variance in the CER are less, which means it is more consistent with the increased signal strength. Now, to understand how the microphone position measurement error compares with the more commonly understood additive noise, if you can look at these two plots, you can see that it's in the range of about 20, and here when the signal to noise ratio is about 10 or around between 10 and 20, you see that the bands are almost similar. So one could conclude and hypothesize that the measurement error in the microphone position of when sigma squared is equal to 1 is almost equivalent to saying that there is a 5 to 10 dB noise in the original signal. Speech intelligibility is something that can also be computed in a similar way. For lack of time, I would not be explaining here about the speech intelligibility. Nevertheless, to say that it follows trends which are similar to what we saw for character error rates for speech recognition. But I would welcome all of you to look at the paper and get more insights. So in conclusion, what we have done in this paper is we have studied the impact of the error in the measuring microphone position on the performance of multi-channel instant speech recognition. We saw that the recognition error increases uh, as the error in the microphone location increases. And also we showed experimentally that with an increased error in the microphone location, the quality of the multi-channel distant speech recognition deteriorates. We also showed that the microphone position error on a distant speech recognition is equivalent to a closed microphone speech affected by additive noise in the range of 5 to 10 dB. Now, one clear observation that comes out from these charts is that the speech intelligibility and the CER scores do not change much significantly when the error in the microphone position is greater than 0.5. Recall that the sigma squared is the Gaussian variance with zero mean. So indicating that higher degree of error in the microphone position does not deteriorate as much the performance of general purpose AR. More or less, what seems to be happening is the error in the performance of a general purpose ASR sorts of stagnates once the sigma squared is greater than 0.5. This is a very important observation, and which I'm sure will come in handy when one is trying to develop new techniques and algorithms to improve the distant speech recognition and intelligibility scores algorithms in that space. Just to end the thing, this is a collaborative work between Karan Natwani of IIT Jammu and Sunil Kumar Koparapu of TCS Research. Thank you very much for listening in. Hopefully, we'll have some question. You will have some questions for me towards the when we actually meet virtually later sometime. Thank you.